Alright, so the last section that we're looking at is modifying what we did last lesson. So it's still exponential growth and decay, but it is modified slightly because, let's read the little text there. It says, in many situations, it is more realistic to say that the rate of change of a quantity Q is directly proportional to the difference between the quantity and some fixed value. So for example, we're going to specifically look at Newton's law of cooling. If you think of a hot drink, and I was almost going to bring one today, but didn't quite get it all organised. You start with a nice hot drink at maybe 90 degrees. It sits in a room, and depending on the temperature of the room will determine how quickly it cools down. If you put that cup of coffee, hopefully hot chocolate, in Antarctica, it's going to get cold really, really fast. You put it in somewhere in the tropics where it's nice and warm, it's still going to cool down, but it's going to take a little bit slower. So it's relative to the environment temperature, okay? And it's going to approach that temperature, and that's where it's going to level off. So obviously it's not going to get colder than the environment, okay? So for this case, this modified exponential case, we have got a slightly different formula. Now, this one here, the Q equals A e to the KT, that is what we had last time. All we're doing is saying plus B because that is our other variable that is going to be in there. Now, you may be asked to use the equation in that form. Most of the time, that's going to be the most useful way to use it. However, if you see something in differentiated form like this, and you see in the brackets that you have your constant Q, or maybe it's another letter, but whatever your variable, sorry, is not your constant, your variable is in there minus your constant, you're going to know that it's talking about this type of equation. If you accidentally turn it into the ones from the other lesson, then you're not going to get the answer's going to be completely out, okay? Because you're not going to have that extra value in there. Okay, so, all right, it's important to note that the B plus A is going to be your initial quantity, which is when t equals 0. So remember before, whatever was in front of that e to the kt, that was our initial amount. Not so for this one, it's going to be whatever the B plus the A is. Okay, let's go into the examples. The mass m of a particular southern right whale is modelled as m equals 55 minus 54 e to the minus kt, where m is measured in tonnes, t is the age of the whale, and k is a positive constant. Oh, there is a minus in the formula, okay? The k itself will be positive because we've already got a minus in there. Show that the rate of growth of the whale's mass is given by the differential equation dm over dt equals k bracket 55 minus m. I want to show that I can start with my equation for mass, which was m equals 55 minus 54 e to the minus kt, and I want to show that I can get it into that other form that we're given in this particular question. So I need to differentiate it. I'm differentiating the mass with respect to time, so dm over dt. To differentiate the constant, the 55, that will disappear. Differentiating the exponential part, the minus 54 is going to stay there. And whatever is in front of the t is going to come down the front, which is going to be the minus k, isn't it? So a minus k and a minus 54 is going to become a plus 54k e to the minus kt. Remember that that power of that exponential never goes down. It always stays the same. Okay, so I have differentiated it, but it doesn't quite look the way it's meant to look yet. I need to try and get it like this. So what we need to do is we need to take what m is equal to, I'm going to do it over here on the side. I'm going to take that m equation and I'm going to get the 54e to the kt part by itself. So I'm going to get m, I'm going to add the 54e to the minus kt across to the same side as the m. That would be equal to 55. And then the 54e to the minus kt, let's move the m away now, would be 55 minus m. Now the reason I did that was because that 54e to the minus kt is in both my m equation and my dm over dt equation. So see it, let me use a pink highlighter. So there's my 54e to the minus kt, and there's the 54e to the minus kt. If I can sub in what 54e to the minus kt is into that second equation, all I've got is the k, and I'm going to replace the 54e to the minus kt with the 55 minus m over here, that little rearrangement. Okay? And so that kind of helps to show why those original equations I gave you up here in the box, why they work. By differentiating, rearranging, and subbing it back in. Jess?
Why did you get there's now two k's in the second line of the power line? Why did you put the k back up the top?
The k, when you differentiate an exponential, the power never changes. So the minus e to the kt always stays up there in the power. But when you differentiate it, whatever is in front of the t will come down the front, which is a minus k. So the minus k came down the front, which is how this one came down here. That's why there's an extra k in that one. So
you don't minus one like you do it.
No, you don't minus one for exponentials, that's right. So everything else you do the same. So you bring the derivative of the power comes down to the front, multiply it with whatever's there, keep the base, but the power, you don't subtract one, it stays the same. Okay.
Is that just an extension?
No, we are going to do that in advanced eventually, once we do a bit more stuff in there. Yeah. There is some integral, some things on the back of your formula sheet that might help with that.
Are we doing integrals this year?
All right, let's keep going. Let's not distracted yet. Part B. What is the birth mass of the whale? And it even gives you a clue there, i.e. when time equals 0. So all I want to do, yes, is take my equation for m and sub in when t equals 0. So that's the original equation for m, which was the 55 minus 54 e to the minus kt. Now, I still don't know what k is, but whatever k is, when it's times by 0, it's still going to be 0 up there, right? So anything to the power of 0, even e to the power of 0 is equal to 1. So all I get is 55 minus 54, which is equal to 1, which means the mass of the whale when it's born is 1 ton, because tons was given as the unit in the question. Part C, when the whale is 1 year old, its mass is 10 tons. Okay, so it's giving me some information so that I can work out what k is. And it says show that k is equal to ln of 6 over 5. It's wanting me to keep it exact in log form. Okay, so still into the mass equation, the 10 tons, that's going to be the mass. 1 year old, okay, that must be key as well. What was the units of my time?
Yes.
Was in years, so I can use just one. Oh, come back here. 1 year old, that's going to be the t. So let's sub those into the equation for m. M equals 10, and then it's 55 minus 54e to the minus kt. Remember, t is 1, so k times 1 is just going to be minus k. Now, the only pronumeral in there is that k. I just now want to find out what it is. So here comes some logs practice, rearranging things. First of all, subtract the 55. So that's going to be minus 45 equals minus 54e to the minus kt. All right, don't really like the minus sign, so we can cancel the minuses out. And then I would divide the 54 across to the other side. So 45 divided by 54 actually makes 5 over 6, simplifying the fraction. Yeah, all I've done is 45 divided by 54. So it's dividing top and bottom by 9.
Oh, because it's not.
Yeah. Okay, so we have to get it out of exponential form now, which means it's time for a sliding base. We're going to leave the minus k. The base e slides across, which means it'll be log base e, or ln for short, of 5 over 6. It's almost where it needs to be. I still have a minus in front of that k, which means I want to move that to the other side. So let's make it a plus on that side, which means it's minus ln of 5 over 6. Now, one of our log laws, I think it was log law number 3, a number out the front of a log can be moved up to be a power. So that would be k equals ln of 5 over 6 to the power of -1. And a -1 means that that fraction turns upside down, doesn't it? So k is equal to ln of 6 over 5. Okay, it's a little bit trickier to keep things exact, but that's what we needed to do to get that value of k over there. All right, there's still more to this on the next page. You do like?
I understand.
Oh, good.
I'm very
What is the mass of the whale when it is 10 years old to the nearest ton? So now that we know k, we can find any mass of the whale if we're given the time. So we want time to equal 10 years, and we're going to put that into our equation for m. So 55 minus 54e to the minus k, so minus k is minus ln of 6 over 5, that was what I just found, times t, which is 10. Yeah? So you can just type that in, be very careful. Obviously you have got an exponential and a logarithm in there. It is, let me bring mine up. Yes, so you're going to go 55 minus 54 times shift ln brings up the e of minus ln, which would, yeah, there is some cancelling out that could have happened in there, but anyway, we're keeping it simple. 6 over 5, close bracket, times 10. All right, did you all get the same thing? Yes, good. So it's 46.28 on the calculator, but we were asked for the nearest ton, so I'm going to say therefore the whale is 46 tons. Yeah. Part E. If the male southern right whale grows to about 55 tons and the female grows to about 85 tons, determine the gender of this whale, giving reason for your answer. So what happens is, for all creatures, when something is born, it grows quite rapidly as it approaches adulthood. Once it reaches adulthood, it kind of would level off at whatever mass it's meant to be at, right? So what we're trying to see is what's going to happen as the time is approaching infinity. Okay, as the time is getting as big as it can, what is the whale's mass approaching? So that's what I'm going to do. As time is approaching infinity, you could just sub in a big number and see what's happening, but we're familiar with this approaching infinity stuff. The part this is going to affect is the e to the minus kt part of our formula. Now, if time is approaching infinity, okay, think about this. If time is approaching infinity, k is just a constant, remember? Times in by some constant. I really have a power of negative infinity. A negative, really, really big number. E to the power of a negative, really big number would give you what? What would it be approaching? Really, really small number. In other words, approaching 0. Okay, so as time is approaching infinity, that exponential part of that equation is approaching 0, which means, therefore, that the mass of our whale is approaching 55 minus 54 times, now it's usually e to the minus kt, but we know that's approaching 0. 54 times 0 is 0, so that is equal to approximately 55 tons. So it's saying that the whale's mass is approaching 55 tons. Does that make it a male or a female? The male, that's right. So therefore, as the whale gets older, its mass is approaching 55 tons, therefore it is male. That was all that talking about the negative big numbers here. So if I have e to the power of a big number like 100, it's going to be approaching infinity. It's going to be approaching a really big number. But if you have e approaching something that this is not even infinity, but a really small number, that is getting close to 0. Okay, negative power, anything to a negative power, unless it's like a big negative power, I should say, is always going to be approaching 0. For exponentials, for bases of x, whatever it is.
Could you also just work out by looking at 55? You
probably could have seen that in the equation, yes. But you had to, it did say in the question, to kind of justify. You had to show why it worked. So, okay.
How does this work? Like, if you reach 10,000 years, you're apparently still going to weigh 55 tons.
Yeah, well, obviously this is not taking into account that things will die. Yes. Yes. Okay, here comes the Newton's law of cooling part. So this one gets a special mention. It's the same basic formula, but it gets a special mention because it is probably one of the most common ways that this is practically used. So it says Newton's law of cooling states that the cooling of an object is proportional to the difference between the temperature, which we usually call capital T, the temperature, and of the object, and the temperature E of the surrounding environment. Okay, so that's our reference point. So in the differentiated version of the equation, it's cooling. Okay, we're talking about Newton's law of cooling. So the constant is always going to be a negative. So you'll see there's a negative K in here. And you'll see that the constant that we're approaching is given the symbol E in the bracket there. It's the temperature minus the environmental temperature. Okay, you can and you need to be able to translate that into the other type of equation, T equals. Do you want to have a go? T equals, going out of the differentiated version back into our exponential form. It would be our constant, which is our environment, plus the AE to the minus KT.
Where did you get A from?
A is just, well, A is the one that we've always used, or we used. Yep, see A back here. It's the one that's usually in front of our E to the KT. Yeah, it can be different. I'm giving you a general rule here. It can be a different letter depending on what the question says. A is just the one that we've been using, so I kept with that form. Okay, so our question is, a saucepan of water is heated to 95 degrees Celsius. The room temperature is a constant 23 degrees Celsius. So that is important right there, because that's our room temperature. That's going to be our environment temperature.
So that's E.
That's our E, correct. The water cools down to 55 degrees after 5 minutes. Okay, so already I've been given 2 pieces of information here. Might highlight them in different colours for you. So first of all, it says a water of saucepan is heated to 95 degrees. That's information piece number 1, because that's time equals 0, that the temperature is equal to 95. Then it's given me some other information I'm going to have to use after that. It says the water cools to 55 degrees after 5 minutes. Okay, there are 2 different sections, 2 different times. That's going to help me find out the different variables in my equation. I'll read the whole question and then we'll go back. The cooling rate is proportional to the difference between the water and the room temperature. So it's alluding to the fact that this is a Newton's law of cooling. Okay, there is that proportion between them. It says, show that the equation for the temperature is, t equals 23 plus 72e to the minus 0.162 T, where capital T is the temperature in degrees Celsius and T is the time, little t is the time in minutes. Now, if it says to show the equation, it means you have to start with no known variables and show how you put things into it, show how you work them all out. Okay, so my starting equation, the one I've already written up there in blue, is going to be the T equals the environment temperature plus AE to the minus KT. Anytime you hear of Newton's law of cooling, that is your starting equation. Now, the information that I highlighted in yellow told me that when time equals 0, the temperature was equal to 95 degrees Celsius. I also need to know that the environment temperature the whole way through this is going to be the 23 degrees Celsius. Okay, so that was the first bit of information. Let's sub that into our equation. Capital T is 95, environment is 23, A I don't know yet, E to the power of minus K times little t, which is 0. So this little minus K times 0 equals just 0, doesn't it? So I really have 95 equals 23 AE to the power of 0. E to the power of 0 is 1, so it's just 95 equals 23 plus A. And so now I can work out what the A is. Just subtract the 23. A is equal to 72. So I worked out one extra value. I now know that T for temperature equals 23 plus 72 e to the minus KT. Now those of you who are really catching on to this may have already gone, of course it had to be. Do you remember me saying that the two numbers, the 23 and the 72, we called them A and B in the first formula that I showed you? Those numbers always have to add to give your starting temperature, which is 95 degrees. So you possibly could have done it in a shorter way, but it is good to see it when you sub in the T. That's why it works. Okay, and it's unfortunately a common mistake that people will just put the A in as 95, just A, and forget that it actually has to be both of them added together. Okay, and that obviously causes problems. All right, so let's keep going. The pink bit of information, the second bit of information, was when time was equal to 5 minutes, our temperature has now come down to 55 degrees. So if we sub that in, what do you think we're going to be finding now? Okay, excellent. So capital T is 55. Our environment temperature plus 72 for our A, e to the minus 5k. Okay, so k is my only variable in there. Let's find it. Oh, sorry, it's not a variable, it's a constant, but I need to find my only unknown. So first of all, subtract the 23. So that makes 32 equals 72e to the minus 5k. Divide the 72. 32 divided by 72, you can divide top and bottom by 8 and get 4 over 9 equals e to the minus 5k. Time for a sliding base. So the minus 5k is going to stay. I'm moving it to the left though. Sliding the e across to be log base e of 4 over 9. And then to get the k, I need to do ln of 4 over 9 divided by minus 5. Now we could do some fiddling around there with our log laws, but by looking at our equation, it's giving me a decimal answer there. Okay, so I don't have to keep this one exact. I just have to show that I can get that minus 0.162. So at this stage, rather than fiddling with your log laws, just type that one into your calculator. And I did get, sorry, it shouldn't be minus there. It should be 0.1622. It's actually 1622. There's more decimal places there, but we only need it to there. Okay, so we have our equation. Therefore, we've shown it all. T is equal to 23 plus 72e to the minus 0.162 t. That's what I had to show. It was a little bit of work to find all those pronumerals in there, but I did get that equation that I needed to get. All right, we have to do some more stuff with that. Now that we have an equation, what do we want to find? Part B. Find the temperature of the water after 30 minutes. So that is going to be when little t equals 30. Okay, so just subbing that in. Capital T for temperature equals 23 plus 72e to the minus 0.162 times the little t, which is 30. And we can type that in our calculator. If you type it in, hopefully you will get 23.6, and it's degrees Celsius. Please remember to include your units. Part C.
You press LN and then what?
You don't press, oh, you press, you don't, yo, where's my calculator thing? So you're typing in 23 plus 72 times shift ln is what you need to press in, Jess, and then type in your power. Okay, part C. When will the water temperature reach 30 degrees? So that is asking me when will capital T equal 30? And it says give your answer correct to 1 decimal place. So into our equation, capital T is 30 equals, and we're using the same thing over and over again, you should have it memorized almost by now, 23 plus 72e to the minus 0.162 t. And we're rearranging to get the t. Maybe I should let you have a try. Yes? Yes, all right, have a go. I won't talk, I'll just do mine. Got it? Yeah, go for it. Yeah, I can't see it very well from here, but yeah, I think so. Why you got a less than sign in there? Is that a less than sign?
14.387.
Yeah, 14.
Yeah, 14.4.
I got minus 6.
Oh dear.
So you can't have negative time, so that's wrong.
Yeah, something's happened in there. Can you see, look at mine, or do you see a difference in there?
All of it to different things. It's always like
You put
random
LN.
weight of
Yeah, ln is log base e.
62 Like you give an example.
Because our exponential, that is at e, so that's our base that slides
I
across.
got to the fourth one.
Good.
772 equals.
Okay, so it's just your sliding base then. So this stay.
Why can't I slide the E across?
Yeah, I did. I just wanted my to be on that side. I just walked
No,
sides.
no, I did that. But why did you put LN?
Because that is log base e. My base e slides across. Log base e is ln for short.
Oh, yeah.
When you slide your base
I
across,
just put in E. Why can't you?
so it's log base e of 7 over 12. That's exactly the same thing as writing ln of 7 over 12. They are the same thing. So over the short version.
Miss, why do we have to use the E then if we're not really using it?
But I didn't mean here.
No, throughout the equation.
Well, the e is telling you there's an exponential growth and decay. We are using it, we're just rearranging it into log form.
Wait, miss, how come we don't use like, why do we use E instead of like 2 or 3 or some other random number?
Remember we called e the natural log? Okay, so probably in the easiest way to explain it, it is the natural growth constant. Like it is the one that compares best to the situations that we do have in nature.
Oh, okay.
Okay, let's keep going. We haven't finished. Part D. Show that the temperature of the water approaches 23 as T approaches infinity. Okay, so we're now doing one of those infinity things. As T is approaching infinity, what is happening to our equation? Remember, we want to look at what's happening with the exponential. Our exponential is a negative, now it's a negative 0.162 times T. If T is infinity, it's basically a negative infinity. E to the negative infinity approaches 0, yes, same as last time. So that means that our temperature is approaching 23 plus 72 times our exponential part, which is approaching 0. So 72 times 0 is 0, so that means that our temperature is just approaching the 23 degrees, which is totally what we should be expecting, because our hot drink should, or whatever this was a hot drink? Our saucepan of water should be cooling down to the environment temperature. Makes perfect sense, doesn't it? So I'll write a little conclusion there. Oh, that's a new question. Therefore, the water temperature
Yes, it's the last question. It's nothing in there. Well,
And we'll finish this year.
then we can move on to advanced trigonometry.
Wait, miss, what are we doing next?
yes, trig. Question 3. A loaf of bread of 20 degrees Celsius. Okay, so that 20 degrees Celsius is my starting temperature, isn't it? So time at 0, times 0, my starting temperature is 20 degrees. So what that's telling me, it is placed in the freezer. So I'm cooling it down, which this freezer is a constant minus 15 degrees Celsius. That is the E, correct. If it takes 18 minutes for the temperature of the bread to drop to 8 degrees, that's going to be my second piece of information, how much longer to the nearest minute will it take for the bread to reach 0 degrees Celsius? You may assume Newton's law of cooling applies. Okay, so it's, we have to make the equation from those things that we've been given. So I've got all my different colour code in there. First of all, my starting equation for Newton's law of cooling is temperature equals environment plus AE to the KT, or minus KT. When? For cooling, yes it is. Yeah.
Why do we have to, what are we trying to find?
We are trying to find out, when we put that loaf of bread in the freezer, we're trying to see how long it's going to take that bread to get to 0 degrees, which is when it's frozen. How long is it going to take for that bread to get completely frozen? It's going to start cooling. When is it frozen?
So we have to find all the other bread.
Yes, we do. So we're going to start by finding all the other little bits of information. So the first one was the yellow stuff I highlighted, which was at the start, time equals 0. My temperature was 20 degrees Celsius, and I knew that my environment temperature was minus 15. Okay, so that gives me in the equation 20 for temperature equals environment is minus 15 plus AE to the minus K times 0 is just going to be 0 up here. So again, remember that the E to the 0 is just 1. So we have 20 equals minus 15 plus A, which means that A is equal to 35. Okay, so
What's A?
A and the environment temperature together add to give your starting temperature. Okay, so it's minus 15 plus 35e to the kt. Okay, second piece of information, the stuff in pink. And there's a whole big blank page on the next You can go on to the next page here.
Oh, what? Doesn't look like
That's why I left it mostly blank on the back so you can have space to write the rest of this one.
Just like double spaces into this page here.
Well, you will actually probably use most of that space plus what we had, so.
Isn't it equal minus?
Oh yes, thank you, minus. If I don't have the minus in the original, it will come out when I work out my constant, but that's okay, good. All right, so when temperature, I'm now told, the time, sorry, is going to be 18 minutes, and my temperature will drop to 8 degrees. Okay, that was the second piece of information, so we sub that in. So 8 for temperature, minus 15 plus 35e to the minus 18k. Okay, move the 15 across, that makes 23. Divide, yeah, we're finding the k. We're going to divide the 35, which makes 23 over 35. Doesn't get any nicer than that. Here comes the sliding base. Yes. So minus 18k, the e is sliding across to be log base e, but we shorten that to ln of 23 over 35. And then we just divide by minus 18. Okay, so these questions can be long, but hopefully you're seeing they kind of follow the same kind of pattern all the time, as long as you can substitute into these things correctly and rearrange them.
Does it
It did not specify. I did do a decimal though. I kept a few decimal places. I went to 0, sorry, that shouldn't be a minus. 0, I did 3. So 0.0233 is what I went to. 4 decimal places, 3 significant figures. So now I have got all the constants in the equation. My complete equation for temperature is minus 15 plus 35 e to the minus 0.0233 little t. So now,
do we have to remake this again starting from 8?
sorry, 2 questions at once, talking over the top of each other, Ben.
It's at 18 minutes.
It is 18 minutes. What was
we
your
have to
question?
remake the equation from when it drops from 8 degrees to 0.
No. So what we do now is we want to know what the last part of the question was. If I go back here, it says how long will it take for the bread to reach 0 degrees? So I now want to find out when the capital T, the temperature, is 0. And I want to find out the time. How long is that going to take? So 0 equals minus 15 plus 35 e to the minus 0.0233 t. Add your 15 across to the other side. Here we go again. Looks familiar, all this rearranging. Divide the 35. Do your sliding base. And finally, divide your constant, k, the minus 0.0233, and you will get 36.36 minutes. But, no, there's only one tiny little bit, just an interpretation here. Come back here to the question. It says in here, where's my yellow highlighter? How much longer, okay, will it take? So it does, we've already been in the freezer for 18 minutes. How much longer does it need to be in there? Another 18, or actually slightly over 18, but yes, 18.36. Yeah, so it was 36.3. So therefore, it will take approximately 18 minutes more for the bread to reach 0 degrees Celsius. Oh, lovely. you even finished in bell time. There's a little reminder here at the bottom. It says for modified exponential growth and decay, if our growth constant, our k, is less than 0, meaning negative, okay? It means that it's one of the decay questions where it's coming down. As time is approaching infinity, our quantity, whatever it is approaching our environment temperature. If it's the cooling one, it means it's approaching our environment temperature, and that's always going to happen. This means that Q has a limiting value, whether it be the room temperature, a maximum weight or carrying capacity, or a certain population base, just saying that it's approaching that value. Okay, so that's the end of our topic.